Let's start with the second part of week 13. So we will try to solve differential equations like ordinary differential equations with and also IVPs, initial value problems. And the general way it looks like for a second order differential equation is like y double prime plus a y prime plus by is equal to rt, and the rt is the kind of right hand side, and it's the driving force or the input that is applied to your mechanical or electrical system. So if you had this, since the beginning of semester we had used the spring and mass systems quite a bit in our examples. They represent quite a number of real cases, or some electrical systems. Maybe we will give some examples to it too. And in those mechanical systems, let's say you're pulling the spring up and then leaving and then trying to understand the position of your mass with respect to time. And if you want to plot that, you need to really solve this type of an equation. And you had done this before in your differential equation courses as well. And we need generally an initial condition, like what is the positions, what are the positions at y0, or what is the current, voltage, whatever, at time 0. Those are the initial values. And yt, the general, the function that I'm interested in is the output, is the response to the input, and I'm looking for yt in these sorts of examples here. So let's move to the notes and have a look at an initial value problem. So it's like a homogeneous ordinary differential equation which doesn't have a right hand side for simplicity for our first example, and y0 is 2, y prime 0 is 3. So let's take the Laplace of both sides. So left hand side, Laplace of y double prime 5, Laplace of y prime plus 6y, and Laplace of 0. Laplace of 0 is 0 because if I put it into my kernel function, it's going to be 0 times e to the minus ft. That's going to be null, so 0. And if you take the y double prime and expand it, it's s Laplace y prime minus y prime 0. And if you keep these, we can continue one more step. And we had driven this before, so Laplace of y double prime is actually, if you expand the first time and the second time, you will end up with s squared Laplace y minus, if you put the initial values like s y0, what is y0? Y0 is 2, y prime 0 is 3, y prime 0, yes, minus 3, and then continue with the 5 and expand this y prime here, SL Laplace y minus y0, and y0 is 2, 5 times 2 is going to be 10, and it's minus 10 here. So basically what you're doing is you're doing an algebra, okay? And that algebra has a rule, and that rule is set by the derivative of a Laplace. And we had driven that before and put that formula before up in our notes. So you can look at that formula and write this term or this expression right away without going into the hassle too. You can do that. But basically what you're interested in is to pull out all the Laplace of y's, and get the coefficients into order, and look at the remaining expressions and sort the terms. Okay, we will look at this whatever coefficients of Laplace y like a characteristic equation that you have been seeing in ordinary differential equation solutions before. So there's nothing much different, but here we have already incorporated the initial values. If you noticed, right, our initial values are already incorporated within the expression, and once you sort out the terms, the initial values are there. So you don't really have to solve for a general solution and then put in the initial values. You're just going straight with the initial values. Now, if you pull out these two S13s to right hand side, 2s plus 13 over s squared plus 5s plus 6. Now, what do? How can you look at this expression and tell, all right, and the next thing we can do is take the inverse Laplace of this. Inverse Laplace of Laplace y is going to give you y itself. That's the little trick, okay? So I had an expression, an ordinary differential equation expression. I took the Laplace of it, and within that Laplace, I have some algebra. That algebra leaves me alone with the Laplace of y. And if I now take the inverse of Laplace of y, I will be able to get the y. And if I take the inverse Laplace of right hand side, that will be my expression that would lead to the y of t. Okay, so f of t, if you will. And that now is necessitating some sort of a thinking. If you think by just some method, I will show you there over here some little tricks here. But if you really cannot come up with that trick, you can use always the partial fraction expansion method, which is I want to be able to, and let's say if you express this s squared plus 5s and plus 6, since my table is kind of giving the things in s minus a, s squared plus w squared or a squared, so I want to change the denominator of such a function to some familiar functions. If I can do that, then I will be able to express the y by taking the inverse Laplace of right hand side. So which is good. So to be able to do that, I'm going to sort out the s squared plus 5s plus 6 into s plus 3, s plus 2. Okay, so that you can do. I'm pretty sure you remember this identity. Now, the top part and the bottom part, if you separate them out, well, it's still difficult, like 2s over s plus 2 and s plus 3, then plus 13 over s plus 2, s plus 3. Where do we go from there? We don't know, because I don't have a real expression for multiplication of two s's. Okay, two s expression. So I need to sort them into partial fractions like a over s plus 2, b over s plus 3. If I find what a and b's are, then I will be able to take the inverse Laplace of this expression, which looks familiar now because there's a little s shift here, and that will be some exponential function that I'm going to be chasing after. So let's do this. And this is as plus 3a, sb plus 2b over s plus 2, s plus 3. So it means that 2s is equal to the s coefficients, like a plus b. 2s is a plus b. And 13 is 3a plus 2b's. That's it. And if you take out two b's from here, you will end up with 4a's. Is that so? No, sorry. If you take take out the b's by multiplying by 2. That will be 3a minus 2a, that's going to be a. And if you multiply by 2 minus 4, 13 minus 4 is going to be 9. If you plug in the 9 over here, it will be minus 7 for b. So there you are. Laplace of y is going to be 9 over s plus 2 minus 7 over s plus 3. If you just pull out this factor out, pull out the 7 factor out, that's going to be exactly 1 over s plus 2, 1 over s plus 3. And if you remember, e to the at is 1 over s minus a. That's like a shifting for a function like 1. And then in that case, I can express 9 Laplace e to the minus 2t minus 7 Laplace e to the minus 3t. So, and this is already taken the Laplace, I can collect the terms in a Laplace expression, and everything inside the parentheses of Laplace expressions are going to be equal from left and the right hand side. So my original function, output function, is going to be equal to 9e to the power minus 2t minus 7e to the power minus 3t. That's good. That's our result. And we didn't need to plug in the initial values later after solving the general equation, the general solution. So what could you do instead of doing a partial fraction expansion that might take you a little bit of time? I could separate or think like in a little bit clever way. If, for example, on top I separate these two s's like s and s, and use this 13 and take a 3 from that and a 2 from that, there will be 8 remaining. Let's keep that 8. But have a look at this. S plus 3 over s plus 2, s plus 3. S plus 2 over s plus 2, s plus 3. And 8 over s plus 2, s plus 3. So if you cancel out these from s plus 2's and s plus 3's, you will end up with 1 over s plus 2, 1 over s plus 3, and 8 over these two. Now, there's a little more trick here. I need to be able to get 8 out of this. So that can be done because squared terms over here can be canceled out. Like if I multiply by 8s squared, those s squares will cancel out, and I have 3 8s and 2 8s here, and that will remain me 1 8. So this expression can be opened up into these two expressions, and now I can add up the s plus 2 terms and s plus 3 terms. That will lead me to the same equation right there, which I found by partial fraction expansion. So that will be 9 over s plus 2 and minus 7 over s plus 3, which is the equivalent solution. Now, let's go back to our notes and systematically try to understand what's going on after the first example. The plot of the first example is this. So this is my output function that I get from my ODE. Now, how we systematically go over this. So you need to set up a subsidiary equation, which is y, capital Y, which is Laplace y, and it's obtained by sorting out the terms and writing up my equations. And over here on the right hand side, I might have an input signal or input, mechanical input, whatever. And if you collect the y terms, which is Laplace of y, which we did before in our example over here, right? So we try to reach this Laplace y by taking the second derivative and the first derivative properly. And in that case, I'm going to be left with some expression with the initial values expressed and the input function expressed on the right hand side, and Laplace of y expressed on the left hand side, and the coefficients of Laplace y. So I'm going to call 1 over the coefficient of Laplace y the transfer function. This you will use later in your control classes and some other courses. This transfer function is 1 over the coefficient of Laplace y in your expression. If you write them again on top, what you are left with is then Laplace of y in terms of s is going to be the something multiplied with the transfer function. That something is including the initial values, and transfer function times the input function. Let's say you have, for simplicity, initial values equated to 0 in a specific problem. Then the simple equation y equals rq is going to be valuable to find out what you need. Q then can be represented by y over r, which are Laplace of the output function over the Laplace of the input function. So this is another definition of Q transfer function if you don't have the initial conditions set. And then what do we do after step 2? Step 2 is pretty much defined as finding the transfer function, okay? And solution of the subsidiary equation by algebra is going to give you the transfer function and the equivalent y in terms of transfer function and the input. Then what do you do? Usually by using partial fraction decomposition or your wisdom or some tricks, you can find the inverse Laplace by sorting out the s terms over here into a nice and recognizable way. Or you can use a software to find the inverse Laplace of your expression to reach the y of t. That's pretty much our methodology to solve an ODE. How about a non-homogeneous ODE? Let's give an example to that. So I have picked up an example from your book. It's appearing in section 6.2, example 4. It's a non-homogeneous case. How come? I have a left-hand side, y double prime minus y, and the right-hand side is a function f of t. So it's exactly t, right? And, well, that may not be a kind of, I don't know what kind of a physical problem it represents, but it has some initial values, and Laplace of y is defined as capital Y. So if you plug in y double prime and keep the y, take the Laplace of both sides. Laplace of t, we had talked about this before. Let me pick up just as a reminder that we had really talked about it. It's over here, right? T. And we had also driven the powers of t, which we are not interested in this problem, but Laplace of t is 1 over s squared. So I can put in 1 over s squared here. Let me go back to the exact slide that I have to be, okay? So we are here. Now, if you put the y double prime, actually, s squared y minus sy 0 minus y prime 0, and both of them are 1, you can take those ones to the and this is s in that case, and this is 1, and take it into minus parentheses, it's like minus s plus 1, and when it goes to the right hand side, it's 1 over s squared plus s plus 1. And s squared, if you group the capital Y, Laplace of Y, s squared minus 1 becomes the coefficient for Laplace Y. And if you take the inverse of that, 1 over s squared minus 1 is going to be called the transfer function. And if you multiply the transfer function on the right hand side with both the input, which is r, and the initial value related coefficients over here, which is s plus 1, you get this expression. And if you open this up, it looks something like this. It looks ugly in the first, and you don't know exactly how to sort it out so that you can take the inverse of that to get the y, real y of t, by taking the inverse of both sides. But I can simplify this one further and expand this one further. So s plus 1, and this can be expressed as s plus 1 times s minus 1. S plus 1's cancel, 1 over s minus 1 for the first expression. And the next one, I can expand this very simply because I can think about this. I don't really have to do partial fractions here. S squared minus s squared minus minus 1 is going to be plus 1. So this expression is actually equivalent to this expression. Now, let's see minus 1s squared. That's in the table. This is in the table. But this looks a little bit new, like 1 over s squared minus 1. Well, I'm not going to drive this one. This is hyperbolic sinusoidal function. So you can look at that in the table. And if you can spot it, you're lucky. You will be able to plug in right away. If you take the inverse Laplace of the right-hand side, that will be exactly y of t, which is exponential t, right? This is a shifting by 1, e to the t, e to the 1 times t, plus sine ht, right? That you need to look in the table. That's the new thing. And minus t. Yes, I know, because inverse Laplace of 1 over s squared is going to be minus t. So this is our expression. This is our function. And this is our output function. If you input to this system a function like this, then this transformation or this system will transform it to an output like this. And that you can actually summarize as over here. You start from a time domain problem, and you recreate the same problem in S space to create the subsidiary equation, and then solve that equation. Sort the terms you have in your hand into some recognizable terms, and then take the inverse Laplace of it to find your exact solution, okay? Particular solution for those initial values. So initial values are embedded. Nice. And sine HAT is exactly written here as A over s squared minus AT. So the difference between the normal sine function and the sine H hyperbolic sine function is the minus over here. So if you have a minus here, that's sine HT, sine HAT. Okay, so we have opened up one more from our table, and that's pretty much it. The rest I'm not going to open up, okay? And if you plot this output, well, this is how it looks like. Now you have all the tools in your hand from the vector calculus and okay, our classes, if you have followed them, You can plot these types of parametric functions very easily from this point on, hopefully. What are the advantages of the Laplace method in solving the ordinary differential equations? I don't need first solving the homogeneous ordinary differential equation in general form and then go to the non-homogeneous. That's taken care of by plugging in the initial values right away into our problem. And better yet, I can deal with complicated inputs, RTs. The right sides of linear ordinary differential equations, which makes them non-homogeneous, I can handle them very efficiently. And the right-hand side inputs can be quite complicated in different engineering applications. That's the power of Laplace transform. Okay, don't forget this. Okay, the integral. I think I talked about this in the handwritten notes. You can look at page 213. I have just put this to make you aware that the Laplace of a derivative is multiplication by s, sum s, and Laplace of an integral is division by s. You can look at this theorem and look at the examples. And another valuable example in section 6.2, example 6, it's about the shifted data problems. Let's say I have an initial value of the experiment. Let's say I'm doing an experiment and I'm measuring the output. Okay, in the time domain, I'm measuring the output. And that comes out, or I can only measure it at pi over 4, time pi over 4. And in that case, I seem to have no initial values, time zero values, but actually I'm measuring it at a random future time like pi over 4. In that case, I can shift my data. It's not shifting the time, it's not shifting the frequency, it's shifting the data in a sense. So an example of that is in your book. I'm not going to repeat that example over here. And let's say if you can put your time pi over 4 over here, let's say your function is giving something like pi over 2 as in this example. You can plug in these values and shift the whole data to get the initial values and solve an initial value problem as such. Now we will go with what's next is two auxiliary functions. We will talk about two auxiliary functions. Like auxiliary means helping functions. They are helping us to define more complicated functions. Okay, unit step function or Heaviside function is one of them we will introduce today, and Dirac's delta function, and with unit step function next week we will do more stuff, and also next week we will deal with Dirac's delta function, which is also interesting. Now these are good to solve ordinary differential equations with complicated right-hand sides, as I have told before, and there are lots of engineering applications where this happens. Let's say, for example, I have an input, a kind of a driving force for the system, which is discontinuous. It's instead of being like continuously driving the system, it's like an impulse. Okay, I pulse the system, continue for a while, and then drop down. Pulse the system, and then drop down. So it could be even my car, an electrically driven car, to which I'm inputting with the gas pedal something, then pulling it back, something, pulling it back. It could be acting for some time only. It could be acting for a continuous longer time, and so on. I could be dealing with cosine and sine functions in these types of situations, and Laplace, instead of Laplace transform for simple cosine and sine, you can use another version of these, which is called Fourier transform. But Fourier transform is only valid for sinusoidal functions, which is like cosine and sine. But maybe I have a more general input compared to these like simple sinusoidal waves, like the one we saw, exponentially decaying cosine sine function, right? In that case, that periodic input, let's say it's a damping input, um, then can be considered only with the Laplace transform, but not the Fourier transform. If you go to some of those intuition videos on YouTube, you can see the connection between this type of connection between the Laplace transform and the Fourier transform. Fourier transform is only valid if you, for example, have, the variable s. We have defined it for our Laplace transform, but we didn't really talk about it in terms of it being imaginary number or a complex number or not. We have been assuming that it's some number, that s, okay, s variable here that we have been talking about. Oh, I closed it again, but it's this Laplace expression that we have. I don't know where I have it lost. Let me put that to give you a rest a little bit, and then of course I went all the way back. Well, I really don't have it in the over here. Sorry, it's on the handwritten notes. In any case, I should put it here somewhere. It's this f of t times e to the minus st dt, that integral starting from 0 to infinity, that Laplace integral. That actually, instead of s, if I put an imaginary number, that would be the same as Fourier transform. But if besides that imaginary number, if I have a real number which makes it a complex number, like that s variable, if it's a complex variable number, then that real part puts me into trouble in your Fourier transformations, and that can only be solved by Laplace transforms. Okay, so that's kind of the connection. Sorry for this hassle here. So impulsive forces, like acting in an instant. So if I just punch with a hammer, if I hit with a racket a tennis ball, those are some functions that can be expressed by the Dirac delta function. But here we will introduce this week the unit step function, Heaviside function. And let me give a little break here to open. So sorry for that. I had to find my handwritten notes one more time. So let's see what's a unit step function. It's called also Heaviside function, and it's also called second shifting theorem. Why it's second shifting? First shifting theorem was in the frequency domain, and it was called S shifting. Here we call it T shifting or time shifting if we name T as time. So this is where the real power of Laplace transform appears actually. So I'm going to denote this unit step function as UCT, okay? And C represents here at the C or until C. T less than C, my function is going to be always 0. But right after C, okay, and equal to C, so my point C is included in the second part of my piecewise function, I have at the C the function rising up to 1. Okay, this for example is equivalent to a signal that is like 0 0 0 0 0, and at an instant at one point C it becomes 1. So it's like 0 1 0 1. It's, you might really actually understand that I can even use this as a signaling in some circuits that are used in computers hardware. And let's say I have a function that goes like 2 2 2 2, and at pi suddenly drops down to 0. How would I express that? So I can write it as 2 minus 2 unit function at pi, unit step function at pi. And let's check whether if this is true. At t values less than pi, this u is gonna be 0. So 2 times 0 is gonna be 0. The function will be just 2. So f of t will be 2. Is that so? Yes. Until pi, my function is just 2. At pi and after pi, that function is gonna be just 1, which is u after pi is going to be 1 times 2, and 2 minus 2 is going to be 0. F of t is going to be 0 after pi. So I can use my unit function to express interesting step functions that can be related to that, and that will be my fundamental function. So I will find the expression of my piecewise unit step function in my kind of complicated signal function by some means. So we can use that property quite nicely. And let's say if I have a general function f of t like this, and I'm gonna try to cut this function from, or let's see, let's first shift it by c, okay? I'm gonna shift this whole function f of t by value of c to the right hand side. In that case, my new function is called f of t minus c, naturally, okay? It's this yellow function here, starting from here. And its initial point is shifted like some constant, which is c. And at c plus 1, which might be here, the function will take on the value f of 1 from that point on. But everything before c, after shifting, I want to be able to cut that signal from my function. How do I do that? I will multiply my shifted function, time shifted function, with the unit step function at c. Okay, so what does it do? Up to c, everything will be nullified. It will become 0 because of my multiplication, and up to c it will be 0 times my function, which is 0. And after c, it will be 1. This unit function will become 1. 1 times my shifted function, it will be f of t minus c. That's good. So let's take the Laplace of this to see what happens in a time shifting. Why? Because I'm really wondering about not the frequency shifting, but the time shifting. And to reach that, I'm going to take the Laplace of time shifted function over here. It is going to be entering my kernel e to the minus st times unit function f of t minus c. I'm going to need a change of variables here. I'm going to change the variable t to some variable x, and that I'm going to call t minus c. X is t minus c. dx by dt is going to be 1. dx is equal to dt. So over here, I'm going to replace dt by dx. And the boundaries t equals 0. At t equals 0, uh, uh, I have, sorry, at t equals c, sorry, at t equals c, maybe I should write c here. Okay, at t equals c. My variable x will become 0. Okay, that's a good one. And as I sweep time from 0 now, because before 0, right, before 0, everything until, before c, everything until c is going to be 0. This function on its own does that. So my integral, which was starting from 0 to and going to infinity, now can be expressed as going from c to infinity. I don't need to deal with the stuff before c. So until c is going to be 0, not going to include that part, and I'm going to include the part with 1 after c. Okay, and that will be equivalent to multiplying f of t minus c by e minus st. So instead of t over here, I'm going to now plug in x. X is t is x plus c from here. T is x plus c, and t minus c is x. dt is dx. So here, and my initial boundary will be t is equal to c. When t is equal to c, x is equal to 0. X goes to infinity. So if I sort the terms by expanding this over here, minus sx minus sc e to the power these times f of x dx. Now, if you take out this term, which is looking like just like a scaling factor, e to the minus sc, 0 to infinity, I'm left with some expression that looks pretty much similar to something we have already in hand. This is my kernel function, kernel integral, because it doesn't matter now if I replace x by y, y by t, or t by x. It doesn't matter. Whenever I put t over here, this looks like my kernel. So that kernel, whatever that variable is, what does this do? That independent from my variable, that's the essence of transformation, independent of which variable I'm using, it changes into another variable which I'm familiar with. In this case, it's s. Capital F of s is hidden here. So I'm going to rewrite this expression as Laplace of ft, because it's again equal to f capital S, the Laplace itself. So, but what do we have added by time shifting? I have an added component like e to the minus sc. So the amount of shifting inverse, like the negative of amount of shifting, is coming here as an expression, or as an exponential over here as e to the minus sc right here. Let's do an example. I have two pi's t and sine t minus 2 pi's. So obviously this is time shifted, and with the utilization of a unit step function, I'm going to be able to cut that function from 2 pi's. Okay, and before that point, the Laplace is undefined. Actually, that's the other little little side information which I'm not going to cover in this course. But basically, what your unit function does is to get rid of the tail, which in which your function is basically not defined. Okay, so or the range that you're interested in. So what does this mean? A time shift, and e to the minus 2 pi s is coming from here. My c in this case is 2 pi's, and L sine t. What is sine t Laplace? Is gonna be 1 over s squared plus 1. So my Laplace for the time shifted sine function is gonna be e to the minus 2 pi s over s squared plus 1. So we will see more complicated signals that could be time shifted, and we will give some examples of that later next week. And we have seen now just a little introduction to see how to time shift a function by taking the Laplace of its multiplication with the unit step function. So utility of unit step function in the time shifting is quite obvious if you consider our example before. So this is the end of week 13, and we will continue with similar stuff on Laplace transformations next week. So see you.